All right. Okay, so I'm going to be hopefully telling you a little bit about how one can create Majorana fermions in condensed matter systems, as well as how you can measure these using scanning tunneling microscopy. So I am not sure of the length of this talk because I tried to combine two different talks. The first part of the talk is going to be focused on observing both bound state Majorana fermions as well as propagating Majorana fermions in this superconductor iron selenium tellurium. It's an alloy. That work was done by Zhenyu Wang and George, who were members of my group. And we had a bunch of theory help from Taylor Hughes and Dirk Moore. And we got very beautiful single crystals. You'll see why this is really important from Gendagu and Brookhaven. And if I hope I can get to the second part of the talk, which will be on this new compound called uranium tellurium 2. This is an example single crystal. And this work was done was spearheaded by my postdoc, Lin Zhao, with the help of graduate students Sean Howard, Zhenyu Wang, George Rodriguez, and Uva Aishwarya. And we had a bunch of theory help again from Ziqiang Wang at Boston College, Manfred Siegrist. And we're currently working with Barry to try and actually understand this data a bit more, because I hope I can get to it. It's quite mysterious. And we have beautiful single crystals provided by Sheng Ran, who was actually a postdoc in Nick Butch's group at NIST. Okay, so just to start at the beginning, it was 1928 when Paul Dirac wrote down his very famous Dirac equation, which combines, quantum mechanics with relativity. So he was trying to write down an equation that was Lorentz invariant and could describe relativistic particles. And once he wrote down this equation, and so here's the Hamiltonian for massless Dirac particles. You can easily solve it and figure out the eigenstates of this Hamiltonian as well as the energy eigenstates and eigenvectors. And you can see that the dispersion for this Hamiltonian is linear. And if you add a mass, so here's a mass term, you get massive Dirac particles. And the dispersion looks linear at high energies and sort of rounds out at low energies because of the mass. But in any case, the moment he wrote down this equation, it was very clear that you get two kinds of solutions. One is positive energy solutions and the negative energy solutions. And the negative energy solutions are now, as we know, are antiparticles. When Dirac wrote down his equation and realized that you could get these antiparticles, it took him a long time to actually understand what these antiparticles were. And at first, it's funny, but at first, just historically, they thought that perhaps, you have protons and neutrons, and perhaps those two are particle and antiparticle versions of each other, but it was quickly clear that that was not the case. In any case, it's really amazing to see the power of writing down a simple equation. And in 1937, which is not even 10 years after Dirac wrote down the Dirac equation, Majorana came up with a different equation whose solutions are fermions that are their own antiparticles. So this is the equation this is this result of his equation. You have particles that are their own antiparticles. The interesting thing about these fermions is that they're actually neutral objects. And so they're spin half particles. You need them to be neutral because otherwise usually antiparticles have opposite charge to the particles. So if you have these neutral spin-off half relativistic particles that are their own antiparticles, it turns out that this is perfectly allowed in our universe, But the point is that all known fundamental particles are Dirac fermions, and we've so far not been able to find any Majorana particles in nature. One candidate Majorana particle is the neutrino. And so this has been a very big question. Could the neutrino be a Majorana fermion? And in fact, there's very extensive experiments designed to answer this question. One of these experiments is this one. It's called the Majorana neutrinoless double beta decay experiment. And if you, I don't really want you to read this, but you can see that this is a very big experiment. You need 40 kilograms of germanium. You have to be underground. And this is called the Majorana demonstrator. And I'll just tell you, the one thing interesting about this demonstrator is that all it does is it sets the stage for an even bigger system, which will eventually demonstrate whether neutrinos are Majorana particles or not. So this one does not do the trick. So the question is, are there any other ways to realize Majorana modes? And of course, one way we know now is by looking at quasiparticles in solids. One example is if you have a spin orbit coupled nanowire, and I'll show you what I mean. It's just a nanowire which has strong spin orbit coupling, and you put it on top of a superconductor, and you turn on a magnetic field, a horizontal field, then theory tells you that you can get Majorana bound states at the ends of this nanowire. And remember, these are bound states, meaning that they're trapped at the ends. These are not propagating Majorana fermions like you would have in nature. So that's just one example of how you might be able to get these. Now, the question is, why is realizing Majorana fermions so interesting? One thing is these are fundamentally interesting, of course, from a physics perspective. Majorana fermions are non-abelian particles. If we can actually realize and manipulate Majorana fermions, we can understand much more about their physics. The other reason that people have been very interested in these Majorana particles is that they can be potentially useful as qubits in quantum computers. Now, these qubits that you might realize using Majorana modes, they're not universal, so you can't use them to perform all the functions in a quantum computer, and yet they are sufficient. So you can actually use them to perform, to make some gates. So just as an example, so here are two nanowires. Here's one and here's the other one. You have, let's say you've trapped Majorana fermions at the ends of these nanowires. Then you can construct a sort of a model where you can ask the question, what happens when you exchange either these two or these two and so on, and exchanging these Majorana modes can actually give you gates. So one nice thing, so I'm not an expert on quantum computation, but the one thing I do want to point out is that these Majorana, each Majorana, you need to make an electron, you need two Majorana modes. And these are well separated in space. So usual excitations of the system, which couple to electrons, are not good at dephasing these Majorana particles. So in some sense, these qubits are extremely well protected. So let's ask the question. So I've just given you a sort of a glimpse for how you create these Majorana particles. Let's ask a deeper question. Why is it that you can actually create Majorana particles in the solid? How does this even work? So here's the equation that you want to satisfy. You want to create particles that are their own antiparticles. That would be the case at zero energy, for example. So if you put E equals 0 here and here, you get a particle that is its own antiparticle. At higher energies, of course, you have to go to opposite energies to get their antiparticles. In any case, if you want to satisfy this, one immediate thing to see is that this requires particle hole symmetry. So that says that, you know, a good place to look would be in a superconductor. So in a superconductor, the excitations of any superconductor are Bogoliubov quasiparticles. Each Bogoliubov quasiparticle is a superposition of an electron and a hole, and it can be written like this. So here's the electron part of it, and here's the hole part of it. And the UKs and VKs give you the weights, the relative weights of the electrons and the holes. So if you want the creation and annihilation operators to be the same, so if you want to set these to be equal, then you can see that what you would like is for UK to be equal to VK. And imagine that it is this kind of thing is possible in a normal superconductor. But even if you could do that, we do have a problem. The problem is for these two to be equal, you look at this creation operator. This is a spin up particle, and this is a spin down particle. So these two spins are actually flipped. So normal Bogoliubov quasiparticles of regular S-wave superconductors, for example, cannot really be Majorana fermions. And so what you really need to do is to actually eliminate spin as a separate degree of freedom. That's what you would like to do. So before I go ahead, are there any questions?
So Paul asks, do neutrons fail to be Majoranas because they are composed of charged fermionic quarks?
Yes.
Okay.
I just responded to that. The neutrons are baryons and have baryon number. And the anti-neutron has opposite baryon number. It's also neutron. Because they are not Majorana.
Correct.
Thanks, Eduardo.
So is that it, Elizabeth?
Yep, that's it.
Yeah, I just tried to see if I could look at the chat, but not easily. Even if I get out of this full screen mode, it's not that simple. Okay, so I'll just keep going. So how do we, so let's say we want to eliminate spin. You know, I'm not saying we should get rid of spin. We just want the spin to be not a separate degree of freedom. For example, if you have spin momentum blocking, then you can describe everything in terms of the momentum of the electrons, and then spin is no longer necessary. So how do we do this? What are the platforms where you can eliminate spin as a separate degree of freedom? One is you can use a spin triplet P-wave superconductor. So we're used to singlet superconductors where electrons pairs are made out of spin up and spin down particles. But you can also have triplet versions of these where the electron pairs are actually equal spin. And in such spin triplet superconductors, you can show quite easily that the excitations of the system are actually Majorana modes. The problem with triplet superconductors, of course, is there are very, very few very few established P-wave triplet superconductors that we know of. I hope at the end of the talk, when I talk about uranium tellurium 2, that you know, I can sort of show you data on one putative P-wave superconductor. Another way of getting a Majorana mode is to use the geometry I talked about earlier, where you have a semiconducting wire with strong spin-orbit coupling. And I'll show you in a second why spin-orbit coupling is important. You place this on an S-wave superconductor. And in this case, you can realize Majorana modes at the ends of this wire. So how does this happen? Well, let's say you have very strong spin-orbit coupling. So without spin-orbit coupling, these dashed, in the presence of spin-orbit coupling, the dashed lines that you see here, these are the bands of the semiconductor, right? This Rashba split by spin-orbit coupling. Now, if you have either a magnet or a magnetic field, you can actually create a gap at this band crossing. And so these are the gapped states. And now, if you have strong spin-orbit coupling, you immediately realize that these bands that you have here, this one and this one, they are spin momentum locked. Okay, So now if you can place your Fermi energy here, you're intersecting only one of these two bands, and this particular band has spin momentum locking. And therefore, you've really created all the conditions you need to get Majorana bound states. And now you take this particular material, there's no superconductivity here yet, and put it on an S-wave superconductor, and then you'll create a gap right at the chemical potential or the Fermi energy. And this material and this system will have Majorana bound states at the end. So this is how you create Majorana bound states. Now this has very complex geometry. And so another way to get Majorana modes is to use topological insulators. And just a quick refresher, a topological insulator has a sort of odd Z2 in its bulk. And because of the odd topological number Z2, you must have surface states on the boundaries of the system. So for a three-dimensional topological insulator, the boundaries are two-dimensional surfaces. And on these two-dimensional surfaces, you must have a two-dimensional gas of electrons. Now this two-dimensional gas of electrons that lives on the surfaces has very interesting properties. It has Dirac dispersion as well as spin momentum locking. So just to give you a sense of how these surface states are different, so you can have conventional surface states with parabolic dispersion, and at each energy and momentum, you would have two electrons. If you turn on spin orbit coupling, like Rashba spin orbit coupling, then they would split in the way that I showed you before. Now at each energy, you still have these two electrons, right? They're just at different momenta. But for the surface states of a topological insulator, if you pick an energy and pick a direction, you have only one electron with a very well-defined spin. So this is sort of an ideal system to create Majorana modes. In fact, Charlie Kane and Liang Fu proposed as early as 2008 a geometry where you could realize both Majorana bound states as well as propagating Majorana modes. So here's the geometry. You take a topological insulator, so right on the surface, all these boundaries, they have this two-dimensional gas of electrons. And then you approximatize the 2DEG with a superconductor. And then they were able to show quite easily that when you turn on a magnetic field, inside the vortex cores of this topological insulator, you will see Majorana bound states. These are zero energy Majorana bound states. So this is one geometry where you can realize Majorana modes. They also showed that using the
really a question.
Sure.
The superconductor is supposed to cover the entire surface, right?
So you can do that. The reason I'm showing it to you this way is if you have a superconductor proximatized in this way, within a coherence length, right, you still have superconductivity. You want to induce superconductivity on the surface of this topological insulator. So it's for STM, this would work, right? You want to look at these vortices, so you can sort of go very close to the superconductor and look for the vortices close to this boundary. But obviously,
you're not looking in the bulk. You're not looking in the bulk of the superconductor then.
No. You want to look at the surface.
No, I understand. You're at the surface, of course, but the superconductor is supposed. I thought it was supposed to cover the entire surface, and then you apply a magnetic field. Right?
You can cover the entire surface with a superconductor, and then it's the same idea. The boundary would become the boundary between the superconductor and the TI. The surface states would become effectively spinless P plus IP, and you turn on a magnetic field, and you'll get Majorana bound states. Yeah.
Okay.
I'm just showing you this geometry because for STM, that's not a nice geometry. So if you have it this way, within a very short distance of the superconductor, you still expect to see the same physics. That's all I'm saying, because of proximity effect. Eduardo?
Okay, okay.
Okay. Okay, so another thing you can do is if you could engineer the system such that you have two superconductors and separated a little bit and with a phase shift. So you want to have some kind of ideally a pi phase shift between the two superconductors, or even if you don't get pi, any phase shift between the two superconducting autoparameters, then they showed that at this boundary, you would get propagating Majorana states. So those are the two geometries. Now, can these two realizations of Majorana fermions be useful? And the answer is, according to Shouxin Zhang and his group, they published a paper in 2018 where they suggested that yes, both these geometries can be used for quantum computation. I'll just quickly show you these two things. So one is that you can take these vortices and you can braid them and you can do quantum computation in that way. And the other geometry is, this was using a quantum anomalous Hall insulator, but the idea is the same, whether you use a topological insulator or a quantum anomalous Hall insulator. The advantage of a quantum anomalous Hall insulator is that you get chiral Majorana fermions at the edges, whereas for the geometry I was showing you earlier, you actually get helical Majorana fermions. In any case, they could show that both of these geometries can be used for quantum computation. And this is the reference, so if you're interested, you should look up this reference. So until a few years ago, most of the experiments done on these on these two geometries were actually transport experiments, because this is a very complicated geometry, and as Eduardo was pointing out, usually you cover the whole surface with a superconductor, and then for STM, it's really difficult to access this interface once you do that. So, but in 2015, there was the discovery of this very interesting material. So this material is known to be superconducting for many, many years. But what they discovered in 2015 is that this material is also topologically non-trivial. So what they found doing band structure calculations is at the gamma point of the Brillouin zone, one of the bands shows band inversion. And band inversion is necessary for getting non-trivial topology. So they showed that the bulk of the system is topologically non-trivial. So this is a great system. It's an S-wave. It was known to be an S-wave superconductor. The bulk is topologically non-trivial. That means that you should have non-trivial surface states. So this is almost like a two-in-one system, and almost an ideal system to realize both vortex core Majorana bound states as well as these propagating Majorana modes. So the question we would try to answer is, can we see signatures of Majorana fermions in this particular material? So here's the phase diagram. Iron telluride is not a superconductor. It's actually a spin density wave material. Iron selenide is a superconductor. And actually, the calculations show that it's in between for this alloy, almost 50-50 alloy, that you, nearby this composition 50-50 is where you have band inversion. So for a range of compositions near 50-50, you have band inversion. This is a crystal structure. There's a reason I'm showing you this. It's because for STM studies, we actually cleave the material. We, when we cleave these layered compounds, you expose one of these top planes. And the top plane here is selenium atoms. So when we cleave this compound, it cleaves right here, exposing the top plane of selenium atoms. Notice that the unit cell, though, is much bigger because the unit cell has to contain both the top selenium atoms as well as the bottom selenium atoms. So this large square here is the unit cell. This is the band structure. It has many bands. It's important for you to know this because when I show you the STM spectra, you'll see many coherence peaks. And each of these bands, it's known from ARPA's data that each of these bands actually has a different gap magnitude. So for example, you have the alpha, near the gamma point, you have the so-called alpha band and the beta band. And then at the end points, you have the gamma band. Band inversion occurs at the gamma point. So it's actually this band and this band that as you add more selenium, they meet and then they open up again, creating band inversion. So this is where you expect to see the topological surface states. So there was very nice ARPA's work done on this material that showed that, so this band here is this band in white. And this is the gap in between these two bands. And in the gap, you can see states that have linear dispersion. These are the Dirac electrons on the surface of this material. So we use scanning tunneling microscopy. So the question we were trying to answer really is this material topologically non-trivial? Do we see evidence for surface states? Can we see Majorana bound states? Can we see propagating Majorana fermions and so on? So STM is a very, most of you know STM. I'll just go through this very quickly. What we do is we bring a tip to within a few angstroms of the surface, and we apply a small potential difference between the tip and the sample. And when we do that, electrons tunnel from the sample to the tip or the tip to the sample, and we measure this tunnel current. Our experiments are all done in ultra high vacuum at very low temperatures. Most of the experiments I'm going to show you today were carried out at 300 millikelvin. So the STM technique is very easy to visualize. When you first bring the sample and tip in close proximity, the Fermi energies of the two line up. And then when you apply a potential difference between the sample and the tip, you can imagine in this case, for example, electrons can tunnel from the filled states of the sample to the empty states of the tip. So the tunnel current is just proportional to the integrated density of states of both the sample and the tip. And we take great care to make sure that the tip density of states is featureless. So essentially, you can think of the tunnel current as being proportional to the integrated density of states of the sample. And so to measure the density of states, what we do is measure the differential conductance, or DIDV. So if you measure the differential conductance of a simple metal, you would see a flat density of states going across the Fermi energy. The Fermi energy of the sample for us, by the way, is zero bias, right? So if you see zero, that's EF. And for a conventional S-wave superconductor, you will see a complete gap, that is zero density of states going all the way up to the gap edge, and then sharp coherence peaks right at delta on either side of the Fermi energy. So these are the STMs we have in my group. And this is the system which goes to 300 millikelvin and has 11 Tesla magnet. And most of the experiments were done using this particular system. Okay, so when you cleave the sample, I said you cleave it right here, you expose the top selenium plane, and what you should see is a square arrangement of the top selenium atoms. You don't really see the ion atoms, and you don't see the selenium underneath, okay? So that's what you expect. And so here are STM topographies of this particular compound. But the reason I show you these topographies is to show you that very often when you grow this material, you can have a lot of excess ion, and you can see all these little dots here, they're all excess ion. And the sample can look not so great. And you can anneal the sample in oxygen to get rid of this excess ion, but still the sample looks awful. And in fact, the superconducting gap doesn't look anything like the gap I showed you earlier with sharp coherence peaks and the density of states going to zero. Okay, even after annealing in oxygen, the density of states doesn't quite get to zero. But we got some really beautiful samples from Genda Gu's group, and you can see in this entire field of view, there's perhaps one ion, or maybe there's one more here and here, maybe 3 excess ion impurities, and that's it. And if you actually zoom in, you can see how beautiful this crystal is. You can see the square arrangement of the selenium atoms. Remember, this is an alloy. It has both selenium and tellurium, and that's what accounts for this inhomogeneity that you see. So even in the dark areas here, you have atoms, and so you have almost a 50-50 concentration of selenium and tellurium. Now, if you take a line cut for this sample, so you take spectra along this line, and this is what the spectra look like. You can see a beautiful, this gap goes to 0. The density of states is 0 here inside the gap. And you can see sharp coherence peaks. But you also notice that we have many different coherence peaks. So for example, you can see up to 3 coherence peaks at these low energies. And in fact, if you look more carefully at higher energies, also you see a coherence peak, but I'm not going to talk about that. So you have multiple gaps, and the gaps themselves are inhomogeneous. So if you look at the literature, look at specific heat, RPS, optical conductivity, and so on, basically you come to the conclusion that the alpha band gap and the beta band gap are 1.5 and 2.5 millivolts respectively. RPS also has measured this topological surface state that I showed you earlier, and that gap is 1.8 milli electron volts. So essentially, within 3 MeV or so, leaving aside the gamma band, you should see 3 gaps if there's indeed a surface state. 3 distinct gaps, 1.5, 1.8, and 2.5 MeV. So what we did to confirm that we have the surface state is we took what we call a gap map, which is we take this field of view, and for every, let's say, 256 by 256 grid, we take a spectrum, and then we analyze all the gaps for each spectrum. And my student wrote a beautiful program to do this, and if you do that, this is what we get. This is called a gap map. So this basically shows you the distribution of gaps in this area. It's pretty inhomogeneous. If you look at the gap histogram, so at low energies, you get these 3 distinct peaks in the gap histogram. And if you look at the mean values of the gap, we get 1.3 for 1.8 and 2.4 milli electron volts. So that's what it is then. So we have 3 gaps, and we can, by comparison with RPS, we can attribute this low energy gap to the alpha band gap, the 1.8 millivolt gap to the topological surface state gap, and the 2.4 millivolt gap to the beta band gap. Okay, so now we've actually confirmed that we do indeed have a surface state with the right gap magnitude. We can ask what happens when you turn on a magnetic field. You expect to see a sharp peak inside the vortex core. So the way we actually locate these vortex cores in STM is by looking at excess density of states inside the gap. So here, for example, in the not so clean sample that I showed you earlier, if this is a DIDV map at the Fermi energy. Normally, in the absence of an magnetic field, this whole field of view should have been dark, because you shouldn't see any density of states whatsoever at the Fermi energy. But now, in the presence of a field, the field penetrates at these points, and you have vortices, and so that's what we see in this field of view. If you go to the cleaner samples, you get a better looking vortex lattice. So this is almost a nice hexagon here. The vortex shapes look a little bit better. And now if you zoom into one of these vortices and take a line cut, so here's spectra obtained along this line, and right at the center of this vortex, you see a sharp zero bias peak in the density of states. And this is right at the Fermi energy. Now, we were not the first people to do this. In fact, Hongding's group in China and Hongding and collaborators did this work. They published this in 2018, where they showed the emergence of this peak right at zero bias inside the superconducting gap, inside the vortex cores, right? But one big puzzle in this system is that only 30% of the vortices show these zero bias states. So the question is, why is it that the other vortices don't trap Majorana modes? Okay, so this system is certainly very promising to realize Majorana states. And okay, one thing I do want to say before I go ahead is that when you turn on a magnetic field in any superconductor, you also get a Caroly-Metricon-Desjans states inside the vortex core. And these states can be anywhere inside the superconducting gap. They could also be very close to zero. So this group had to do a lot of work to show that these states that they see close to zero bias are indeed Majorana states. Okay, so certainly our samples are good enough to see the Majorana bound states. And the question—
Vidya, can I ask a question I asked in the chat, but I think you're going ahead without.
Okay, let me actually pause and say, please go ahead, Eduardo, and if anyone else has a question, this is a good time.
Yeah, so why don't you go back to the pictures with the vortices there? There seems to be some structure inside the vortices.
Yeah.
Is that like a vortex halo in VSCO? I mean, do you see a checkerboard or something like that inside there?
So no, actually, this is noise.
That is noise here.
This is noise. And one of the reasons vortices are noisy in STM is because very often they're not pinned. So you can see here, see the streakiness?
Yes.
That streakiness is this vortex actually moving a little bit. And all this noise is because the vortex wants to move.
So, but you don't see a halo effect as it is seen in VSCO?
No, so I don't know if we took good enough data to give you an answer to that question.
I mean, I want to know whether there is some subsidiary order that appears around the vortex.
Right, so in VSCO, you see the checkerboard, right? Inside the vortex.
Is a charge order that appears.
Exactly, the charge order. So the number of pixels, so this is a pretty large field of view, and I don't know if we have enough pixels here to answer that question for you. I think my suspicion is that there's nothing, there's no extra charge order, but sorry, Eduardo, I don't think we have the data to say yes or no.
Okay.
Okay.
Vidya, Dale also had a question.
Yeah.
And he asked, why is the gap map so inhomogeneous?
So we think it might be because it's an alloy. And so let me just go back for a second. So we haven't really done this, but so these dark and bright regions correspond to areas where you have less or more of selenium or tellurium compared to the background. So it's pretty inhomogeneous chemically, right? And it's entirely possible that the gap inhomogeneity is related to this chemical inhomogeneity. In VSCO, for example, that's what people think, that the gap inhomogeneity is related to the oxygen distribution of oxygen inhomogeneity. So we haven't done a cross correlation between this map, the topography, and the gap map. I think we tried to do this, but I'm not sure of the results. But I think the simple guess would be that it's because of chemical inhomogeneity.
So now this is a question from me, not Dale.
Okay.
If that's the case, does that mean that ideally you would want a material where you're ordered instead of randomly placing the?
So if that's a good question. in this case, I don't think it matters so much because you can see everything you want to see. You see the Majorana bound states. You see the, I'll show you later, we think we can see the propagating Majorana modes. You can ask the question, in what way does this inhomogeneity actually affect you? And I don't think it really affects you in any substantial way. One problem with the sample is, like I said, excess ion. I mean, in this sample, we didn't have much of that. But whenever you have that, if you really have excess ion, then it can create trouble for the Majorana bound states. And so that you want to avoid at any cost.
Thanks.
Okay.
I think those are all our questions for now, it seems.
Okay. 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 So then let's try to ask the question, can we see evidence for propagating Majorana states? So let me just remind you, if you have this kind of a geometry, if you have two superconductors with some kind of a phase shift, at the boundary between these superconductors, what you expect to see are these propagating, this is the dispersion of the Majorana states inside the superconducting gap. So this is the gap above the coherence peak above, below, so this is the gap area. Inside the gap, you see these dispersing Majorana states. And Charlie Kane and Liang Fu showed that no matter what this phase shift, you still expect to see these Majorana states inside the gap. The only difference would be whether or not they're linearly dispersing at zero energy or whether they have a gap. Okay, so do we have all the ingredients we need? We have superconductivity, S-wave superconductivity. We have non-trivial surface states on the surface of this material. Now we need to somehow engineer a pi phase shift. And the question is, how do we do that? Jianping Hu and his collaborators wrote a paper in 2013. And it was a paper in general about the nictide superconductors, where they suggested that if you take into account nearest neighbor, next nearest neighbor, and so on, pairing, and you can actually get a very interesting situation where there's actually a phase shift in the order parameter between the top and the bottom selenium layers. So why is this interesting? Well, so this is the crystal structure of the material again. So this is the top selenium and the bottom selenium. You realize immediately that in forming this crystal, a certain symmetry has been broken, because you might have imagined that that this could be flipped, where these seleniums are at the bottom and these are at the top. So that's equally likely. And in fact, you expect to see multiple domains in the system where the top and the bottom selenium atoms actually flip. So if you do have such a domain wall, so this is a cartoon of such a situation. This is a top view, right? So this is all the atoms on the left, this is all the atoms on the right, and you can see that the top selenium has flipped over to the bottom selenium on this side. So if you have such a domain wall, according to Jianping Hu at least, you should see a phase shift in the order parameter between this side and this side. So that's the idea. So here is the beautiful field of view I showed you earlier. There certainly don't seem to be any domain walls here, but because we're doing STM, we can walk around the sample and we can look at other areas. And if you search around a little bit, you can find areas where you have lines on your surface. So you can zoom into one of these areas, and this is what it looks like. This is these are the selenium atoms on either side. This is the domain wall. And you can ask the question, how do we know this is actually a domain wall? Well, first you take a Fourier transform, and in the Fourier transform, these are the Bragg peaks of the selenium lattice, so here and here. But you can see this particular peak has been split into two. And when you have split peaks in a Fourier transform, you know that there's a phase shift between the atomic arrangement on this side and the atomic arrangement on this side. Now, you can't tell just by looking at this Fourier transform whether this phase shift is pi or not. So you can actually try to zoom in and check with your eye, you know, here are the atoms on one side, and as you go to the other side, you go in between the atoms, but this is not very precise. Another way of doing this is simply by using Fourier transforms, because in a Fourier transform, you can get information both about the phase as well as about the position of the atoms. So here, for example, are two lattices phase shifted by pi. The Fourier transform looks like this, and this is our phase map. And you can see going from A to B that the phase shift between these two regions is pi. The difference between this and this is pi. Okay, so we can do that for our domain wall. So here are the two Bragg peaks that are split, and you can do a phase map. And once again, going from A to B, this is the red line, you can see the phase shift between these two regions is pi. Okay, so we have the right sort of domain wall, and now we can ask the question, what do we expect to see at this domain wall? If you have a single impurity, then you get a sharp peak in the density of states right at 0 in this particular system, or you can get peaks on either side of the Fermi energy. So you have these kinds of peaks. So individual impurities give you peaks inside the superconducting gap. How about a step edge? So if you take spectra along this line or this line, you see that far away you see the nice superconducting gap, but right next to the step edge, you see peaks in the density of states inside the superconducting gap. We've also found other kinds of 1D defects in the system which don't show this pi phase shift. And if you take line cuts across these kinds of defects, what you find is a narrowing of the superconducting gap. The gap actually gets smaller. And so this is the phenomenology. Essentially, you either see peaks or you see a narrowing of the superconducting gap. But when we go to this particular domain wall, what we see is really interesting. So this is far away, this blue spectrum. You see 0 density of states, this is 0. And right on the domain wall, you see a flat finite density of states inside the superconducting gap. So you can see this is true. You know, this is a line cut going from here to here. So here's this dark region is the gapped region. And as you go along here, you get sort of a flat density of states inside the gap. So this flat density of states you can show is connected to superconductivity, because so here's another domain wall, not the same one. You can see the flat density of states. This is at 1.7 Kelvin. And when you go above TC, basically this shape disappears and you get no features whatsoever near the Fermi energy. So this thing is connected to superconductivity. So this question is, why do we see such a feature? And then you can ask the question, what do you really expect for this scenario if you had such a pi phase shift? Well, the answer is you expect a one-dimensional propagating Majorana fermion. And such a propagating Majorana fermion is expected to have linear dispersion. And so if you have linearly dispersing states inside a superconducting gap, what you really expect to see is constant density of states coming from these Majorana modes. And so that's exactly what we have. We have this constant density of states, which represents the linear dispersion of the propagating Majorana modes that live along this 1D channel. We can do more characterization. We can actually look at how these states change as a function of energy. If you have a topological state, what it's expected to do is as you go from the middle of the superconducting gap towards the edges, the size of this state, the spatial extent, should increase until it fills up the whole space. So this is a DIDV map of a domain wall obtained at the Fermi energy. You can see that the Majorana modes live pretty close to the domain wall. As you increase energy, the spatial extent of this Majorana modes gets bigger and bigger until close to the edge of the superconducting gap, it completely spans the entire region. Okay, so this is the summary. We've studied this alloy, F ion selenium tellurium. We find that if you look at a very particular kind of domain wall, we see evidence for linearly dispersing domain wall states. And all the evidence that we found so far points to the existence of both bound states in the vortex cores as well as linearly dispersing states at these domain wall boundaries. And of course, you know, the next thing would be to use measurement, like do experiments like the ones Dale does to actually measure the non-abelian statistics and try to see if we can braid these Majorana fermions in some way. Okay, so I'm going to pause here. I have only 5 minutes left, and I just want to show you just a few slides on this new superconductor, uranium tellurium 2. But before I do that, I'd like to take some questions, if there are any.
So Eduardo asks about the first picture with the domain walls and how they seem to end in some places. And he's asking that this is not what a domain wall should do unless it encountered a grain boundary or a stacking fault. And is that
correct. So there is something funny going on here. There is something, see this line, Eduardo? So I don't know exactly what's going on along this line, but it ends at this line.
Yeah, so that to me looked like a possible stacking fault or something of that sort.
Yeah,
but there are other ones that seem to end somewhere else.
I mean, there's a certain contrast we pick when we show these topographies. And so I don't know if we picked a different contrast where if this would go all the way to this point or not.
The domain walls either at the end of the boundaries of the system or they close on themselves, right?
Correct. So there's certainly a line here, and so you can imagine that this is actually going to go and end here, and it's just not visible because of the contrast of this particular image. I'm not 100% sure, but I can tell you that the domain walls we looked at that look like this, usually they end at step edges or at stacking faults.
Yes.
That's true. That is correct.
I have some comments on these excitations. Majorana fermions are not non-abelian. There is a confusion in the terminology that people use in the literature.
Okay.
Majorana zero modes at the endpoints of a gapped state. Those actually, at least that's the theory, within the Bogoliubov picture. So remember that there's a partner at the other end of the world, so to speak, at the other end of the wire.
Yes.
And they have these non-trivial fusion rules. They fuse into two different channels.
Correct.
The excitations of a superconductor, at least in the Bogoliubov picture, are already Majorana in the sense that they obey the Majorana reality condition. And there's nothing non-abelian about them. This is a problem. I think the paper by Sucha and Zhang and collaborators, I cannot badmouth a person who died so tragically, but that paper is misguided.
I see.
You cannot braid massless excitations. You cannot do that.
But the ones at the ends of a wire, you can.
Those at the ends of the wire, you can fuse them, and there are these rather elaborate schemes that people like Jason Alicea and others have concocted.
What about the ones inside vortex cores, Eduardo?
The one in vortex cores too, so as you approach two of the vortices, they will fuse either into the identity, in other words, will be like the superfluid, or they will actually create an actual quasiparticle of the superconductor.
Right. You don't want to fuse them, but you can circulate one vortex around another, right?
Well, fusion, yeah, they're related. Braiding and fusion are related concepts. But these gapless Majorana excitations that move, that propagate with a linear dispersion, there is nothing non-abelian about those things.
I see.
They're interesting.
Yeah.
And so if you could then, either with a magnetic field or something, give them a gap, then at the endpoints of these defects, then you will get Majorana zero modes that will behave in the usual topological way. But those of themselves are not non-abelian.
Okay, that's really interesting.
That's why I usually don't call the Majorana zero modes Majorana fermions. They should be called Ising ennions. Okay, that's the proper name. Okay.
Okay, Ising anions.
Sorry, this is a problem. It's an eternal discussion, and it came from the way these papers by Fu and Ken and others actually were written, but it leads to a lot of confusion.
Okay. So one interesting thing I do want to mention here is that we did look at these kinds of domain walls when two domain walls meet at the end. Okay. And you see a zero bias bound state like you would expect, actually. So that's really interesting. So you're saying that those zero bias modes might be
yes,
non-abelian.
But you will want to do something to actually gap out the entire these excitations that actually propagate along your defect.
If you want to use them, if you want to use them.
If you want to actually use this for quantum computing, however imperfect it may be.
Right. Okay. All right. Thank you. Are there any other questions?
So there don't seem to be any other questions right now.
Okay. So I think I've run out of time, right, Elizabeth?
Yeah.
Okay. So what I'm going to do is I'm not going to actually go through the rest. Let me just tell you very quickly in words about this new compound. Uranium tellurium 2, UTE2. It's very interesting. It was discovered to be superconducting. So this compound has existed for a long time, but it was discovered to be superconducting at a low temperature of, not that low, 1.5 Kelvin. And there was immediate interest in this because the night shift showed that there was no change across TC, which is a signature of triplet pairing. This system has a lot of interesting phenomenology. For example, you can ask what happens under pressure, what happens under high magnetic fields. And in pressure, you seem to go from one kind of a superconductor to another. In fact, the TC actually goes up. And eventually you reach some kind of a magnetically ordered phase. Whereas in a magnetic field, at very high magnetic fields, more than 40 Tesla, you see the emergence of superconductivity once again. So they call this a field polarized superconducting state. The specific heat is also interesting. It shows a pretty large jump at TC, but at zero temperature, it shows this huge residual specific heat. It almost looks like it's half the normal state specific heat value. So this is a very interesting system, and I don't have time to go into it, but I just want to show you one slide, and then I will stop. So we looked at the step edges of the system, and we found something really intriguing. So here's a topography. Here's an actual terrace. So this is, this is sort of a line cut. This shows you right at this edge, you go up. This is one atomic plane, and then it's flat, and then you go down, and so on. And if you take spectra along this edge, what you see is really interesting. On one step edge, on one of these edges, you'll see these peaks in the density of states below the Fermi energy. And on the opposite step edge, you see peaks in the density of states above the Fermi energy. And these peaks actually live, so this is the superconducting gap in the dotted line. These peaks live inside the superconducting gap. And the line shape of these features is also intriguing. You get a peak, but you also get a dip on the other side. And the energy scale of the dip and the peak are identical. So this is an extremely particle hole symmetric feature, except it doesn't really have particle hole symmetry at any given point along these step edges. These features are chiral, and if we've done a lot of analysis, and basically the bottom line is that you have these chiral in-gap states, and all the evidence from STM points to having a superconductor order parameter, which has a vector associated with it. Because if your superconductivity didn't have some kind of a vector, you would never see states, chiral states of this kind. In any case, I really can't go on because I've sort of run out of time. So I'm going to stop right here. I just wanted to bring up this material, uranium tellurium 2, and tell you that this might be a really nice example of a triplet P-wave superconductor where you might actually be able to see Majorana fermions at the edges. That's it. Thank you for your attention.
Thanks a lot, Vidya. That was really interesting. I have a question on that last part. Everybody's applauding electronically.
Okay.
So this step boundary, that's a monolayer of the uranium,
yeah, that's
on the bulk.
That's correct. So we often find these naturally. In fact, you can see here, this is a monolayer step up. This is actually a monolayer step down.
So would you see the same thing if you just took a monolayer but on some other substrate as opposed to on the bulk? Or do you think
yes, I think so. Let me think for 1 second. Yeah, so that's a really interesting question. So one of the questions, there are many open questions in the system. One of the questions is this a sort of a 3D superconductor or is it a quasi 2D superconductor? If it's quasi 2D, I think that if you just took a monolayer, then you would see this on the edges. If it's a 3D bulk superconductor, then I'm not exactly sure what would happen. Like if the Fermi surface of this system, we still don't know a lot about this material. We don't know if it behaves like a quasi 2D system or whether it behaves like a 3D system.
Thanks. So I don't see any other questions for anyone, but Eduardo's unmuted himself.
I want to say something. First, beautiful talk and beautiful data, as usual. I really enjoyed it. A word of caution about the, the NMR. Remember that in strontium ruthenate, this was supposed to be the smoking gun for P wave.
Yeah.
And this has gone away now. It turns out that it's not really constant.
Yeah.
And it has, so people have to do a more delicate NMR experiment.
Yeah.
For that.
So they did actually do that. Yes. And what they find is that there's a slight change in the night shift, but that change is, I think, less than 10% of the night shift value. So it's nothing like you would expect for an S wave or a D wave superconductor. So they still believe that this might be a P wave. There's another bit of evidence. It looks like since the material is orthorhombic, it looks like there might be two transitions very close to one another. So there's one transition at, let's say, 1.56 Kelvin and another at 1.5 Kelvin or something like that. And then it's only below the lowered transition that you think that it might actually be P wave.
Look, this is a strong spin orbit material, right?
Right.
So it's possible that there is a mixture of S and P.
It's possible, yes.
Because in the presence of spin orbit, they are not got quantum numbers separately.
Correct.
So it could be that it's a small S wave component, and that's what gives the slight suppression.
Correct, exactly.
Then the interpretation is more delicate. That's what I'm trying to say. It's not
correct.
Clear.
Yes. One thing is that for strontium ruthenate, what they tell me is that the heating effect there is pretty substantial when you do the NMR experiments. Here for uranium ditelluride, the density of states is pretty high. It's actually a heavy fermion system. So the heating effect is not as substantial here. So
these are comparable.
Much more confident of their NMR results.
But the TCs are comparable. That's the only thing.
The TCs are comparable, correct. You're right.
So,
well, thanks everyone for coming. Thanks, Eduardo, for all the questions. Thanks, Vidya, for the great talk.
Yes.
I think we are off next week unless someone volunteers in the next few days, and then we're back in 2 weeks with Edgar.
So should I stop sharing? How do I stop sharing? there. Okay.
All right, thank you, everybody. Great talk.
Thanks. Thanks, everyone.